Today we're going into the mainstream of quantum condensed matter. Until now, basically, the part that dealt with electrons, we ignored the fact that we have a lattice. So all that the matter did was provide a box in which the electrons reside. We used quantum mechanics, we used statistical mechanics to figure out what were the properties of such electrons. We saw something about magnetism, we saw something about heat capacity. We actually didn't say anything about conduction, except for the very early stage where we had Drude theory, if you want to call it that. And there we ran immediately into a problem that there are materials where the charge-carrying particle has a positive electrical charge, and more or less at loss to explain. Okay, so what we're doing in the next probably couple of lectures is to see what is the influence of the lattice. Why are we convinced that the lattice makes a difference beyond some small corrections to the pictures that we presented previously?
What is actually measured?
Yeah, but why is it the lattice? Perhaps it's who knows what.
If it provides another way of interaction.
Okay, but I would want to get a more physical explanation. It's a potential, and that's the way that we see it. But it's a potential that has properties that is different than what we are used to. And that is, we are used to two cases. One, free electrons, and the second, a potential that actually localizes, sets the wave function in a certain region, and that's that. Okay? So let's say the hydrogen atom, we have an electron sitting around at the most a distance of a few angstroms from the center of the atom. On the other hand, free electrons live everywhere. Now we have some strange hybrid of these two situations. We have something that is extended, but it's extended in a particular way. It has a symmetry. We didn't destroy all symmetries. We left a discrete symmetry where if we move from one point to a point that is at the distance of the lattice wave vector, it should be the same environment. Okay, let's consider two properties that we know that are connected to symmetry. One is energy. Energy is something that, what is symmetry that?
Time.
Symmetry in time. No difference between this time and a different time. So, in our system, from the point of view of a lattice, do we have time dependence? At least in the zero orders, no. We know that we have phonons which can change, but no. Therefore, basically, from the point of view of energy, we expect energy conservation. The fact that we have a lattice in this sample won't change. What will break energy conservation? Problems of the type that you never yet handled in quantum mechanics, like an electromagnetic field. There we know that energy can be either dissipated or absorbed from the field, and the game is different. Not that we learned how to do it, but at least conceptually we understand that it's possible. So we still have energy conservation. Our time-independent Schrödinger equation is okay. E is a good quantum number. Now, from the point of view of momentum, what do we know? We know that free electrons conserve momentum. Why is that? What's the symmetry?
Translation.
Translation symmetry. We know, on the other hand, that a particle in a potential doesn't conserve momentum. Why? Because if you translate from here to there, you see a different potential energy. So no reason that the momentum will be conserved. For our lattice system, we have a strange situation. Translation is broken except for some discrete values. If you move from here to another point at distance r, r is a vector of the lattice, then you are in the same direction. So what happens in this situation? We'll see. We have to develop that actually momentum is not conserved. Quasi-momentum, and we'll define what do I mean by quasi-momentum, is conserved. Okay, so you don't think it's some kind of black magic, it's something that you already know.
Thinking about the Fourier transform properties, it should be something of a phase, right?
Mm-hmm.
Because translating the center of Fourier transform, it's
right, and we'll see a proof of that through Fourier transform. But I want to stop and go back to something that we actually did observe quasi-momentum conservation. We did scatter a particle of a lattice. It was light and neutrons. And what did we see there? That
phonons were
okay, let's forget about phonons. The zero phonon case that we discussed. Or even in the beginning of the year, of the semester, the Bragg scattering. What did we see? We had a photon coming in at k and going out at k prime, therefore clearly not conserving momentum, but we still had some kind of rule about it. K minus k prime had to be equal to g, the reciprocal vector. And that is conservation of quasi-momentum, meaning that the momentum of the electron is conserved up to a change in g. So this is the properties that we'll see, and it has effects on a lot of things, some of them very surprising. Actually, in the last few years, there is mapping of all that we did on momentum, all that we will do on momentum, to the second symmetry. Someone heard about time lattices?
Time crystals, yeah.
Time crystals, what is that? That's a system that has a broken time symmetry, but it returns to itself each at certain times. Periodically. Very similar mathematics, very similar type of behaviors that come out. So you have quasi-energy and not energy. Okay, so we are looking into electrons in a periodic potential. So, and when I say electrons, as usual in this year, non-interacting electrons, single electrons, so what do? I write a Hamiltonian. Something should have been imprinted in you in the quantum mechanics course, as we start by writing a Hamiltonian. Basically, this is a very general Hamiltonian. I actually stick in the correct potential energy, and you can have anything from a harmonic oscillator to a hydrogen atom to heaven knows what. So what makes it something relevant to electrons in a lattice? One very simple condition that the potential has to have this translational symmetry in R, large R. That's all I need. I'm not at the moment saying anything about the exact form of the potential, because most of the things that we'll see don't depend on how this potential exactly looks like. It's more that it has this property. Now, in a particular material, of course, it's important. So, just the fact that you have this condition gives you something that you know about the wave functions that solve these types of Hamiltonians, and that's the Bloch theorem. Okay, and I'll state it and then we'll prove it using two different methods. Why? Because each one shows us some aspects of this theory. So, the wave function that can have two quantum numbers, actually more, k here is k vector, so it's actually 4 numbers. We'll see at a later stage what is this n, because the k is very intuitive. It's something that reminds us of a free electron, and as I said, the momentum is important, so K will be in the game. Okay, so I break up the wave function to multiplication of phase and some other part of the wave function. Okay, and one other condition. The non-phased part has to have exactly the same value at each distance r, large r. Okay, why, since the potential has the same symmetry at each point at distance r from each other, why doesn't the wave function have this structure? That only that up to a phase?
Because there's the momentum.
I want even a more general answer.
It's not observable.
It's not observable. The wave function doesn't have to be the same at each point, although all physical conditions around it is the same.
It's like a cylinder, right? And the phase is counting how many.
I have here additional phase that let's take the simplest case. I want the same density at each point at, if I'm looking at point R, or R plus R1 or R plus R2. The density is this guy squared, and this guy squared, if this condition is fulfilled, fine. And what it does, the fact that if I would have only decreed that the wave function has to be exactly the same, basically I would have a state that can't carry current, and that's not true. Same as a free electron can carry current. Why can it carry current? Because there's nothing that stops it from being at this point, the next point, the next point, all of it is okay. Now you can ask, but we know that in potentials that gives me some way of catching the particle, like harmonic oscillator. I'm exactly at the same point. But this is not the case. Remember that in quantum mechanics, somewhere we said that a potential has the wave function has to be real only if the particle is confined into some region. Otherwise, you have to have phase, and that's what you claim. Okay. Should prove it. Okay, one very elegant way is to define an operator. We'll call it the translation What does this operator do? let's.
It's like time evolution, but for space, right?
It does a very simple thing. Takes this operator, we'll use it for R of course, but it could be in principle any. PRZ is applied on some function R, gives me the value at point R plus large R. Okay, principle I could put here R prime, and doesn't have to be a lattice vector, but for our case it's interesting for the lattice vector. I want to prove that this is operator has the same set of eigenfunctions as the Hamiltonian. If you remember, you use the same trick in quantum mechanics, let's say with the parity operator. When we define there that a solution has either odd or even parity. Okay, so how do I prove it? I check what is the commutation relation with the Hamiltonian. So I am using the translation operator on H multiplied by psi, the left side of the Schrödinger equation. Why? Because that's what this operator does. Takes any function, wherever R is written, I write R plus R. This guy, by construction, is the same as HR. Why? Because P is a derivative of X, and for the derivative, the fact that I added some constant doesn't change anything. And this guy is our postulate that we are describing a lattice. And the wave function at the moment, I don't know what it does. Right, by definition. So, this and this are equal, so they commute. So TR works on H is equal to H with the TR after it. Another thing that I know about translation. What else do I know about translation? That if I perform one translation and then another translation, it's equal to the translation of both of them, or in mathematical language, T of R and then T of R prime is equal to T of R plus R prime. Which, on one hand, is trivial, but we know physical quantities that don't behave like that, rotations. That, at the end of the day, is why our angular momentum operators and everything around it is more complicated than just free electrons. So, and in a moment we'll use this. So H that works on psi it's some constant, C of R, I don't know at the moment. What I do know, it's the same psi. Is this correct for any distance or vectors that I'll put here?
No, it should be a lattice vector.
It has to be a lattice vector because this point relies crucially on the fact that it's a lattice vector. Because if I'll just choose some R prime, it won't work. So, let's take this property and see what it says about the eigenvalues of this operator. Well, we saw that T of R is C of R, T R prime and the order is not important. You can first apply one and then the other. It's also equal so this guy and this guy must be equal. Okay. because, as we did in the beginning of the course, because this fulfills this condition. Which is Bloch's theory. The same wave function up to a phase. I didn't say anything about K. If I'll add periodic boundary conditions, then I have a quantization of K. But otherwise, K at the moment can be anything. Well, not exactly anything. Why?
Because to the reciprocal.
Because I can change this K to K plus G and nothing will change. So if I want to look on what are the possible Ks, it's enough that I'll look on the first Brillouin zone, because all others and now I'll say something that we'll see in more details further on. You remember that I started with n of k. The number of degrees of freedom doesn't change by the fact that I have a periodic potential here, right? If I had a free electron in an infinite space, I would have any k could describe it. Here I basically tell you that, well, there's no point, all these k's are the same. So actually, all Brillouin zones still have to contribute. And interesting things, they don't have to contribute with the same energy, although the symmetry has to be the same, and we'll see it described in two different ways, under two different specific potentials. But at the moment, it's just a point to notice. Okay, first description. First proof of Bloch theorem. Very general, is very elegant in the meaning that it captures the symmetries. But I'll go to another proof, which is through the Fourier transform. And it will be very convenient when we'll do perturbation theory. At the end of the day, we won't be able to solve explicitly the Hamiltonian for any potential. But we would be able to do it at different limits, and one of them is that the potential is weak. Perturbation theory. And for that, the Fourier transform is very convenient. If I have a wave function, I'm allowed to Fourier transform it. Will it be helpful? We'll see, but I'm definitely allowed. For a free electron, it's very convenient because I have value 1 for a particular Q and 0 for all the others. If I'm in an eigenstate. If I'm not, so I have here the superposition. Well, I would want to perform a Fourier transform also on the potential. Sorry, it's U of R, of course. What is U of K? Well, in principle, I can write down an integral over all space. But since at each cell it's exactly the same behavior, so I can integrate over one cell. And divided by the volume of the cell. As usual, in in things that are connected to Fourier transform, I can put the volume in one of them or divide it by a square root, but it's my decision. As long as I'm consistent in using the definition, it doesn't make a difference. So here I chose to put the volume here. Okay. Since I have here a cell, I can have an average value of the potential. Does the average value of the potential make a difference physically?
No, because it's a constant.
No, the same thing as if in a problem where I had, let's say, a free electron in a potential that was some constant. Everything is shifted by the constant, but the nature of the solution doesn't change. So to simplify my life, just decide to set it to 0. Why it's u of k equals 0? That's something you should internalize and should become a second nature for you. The average is always the zero mode of the Fourier transform. Why? Because if you put here 0, you're just integrating over the function. No phase. So it's the average. So for any Fourier transform, u of the function at k, or the component of k equals 0, is the average. If I'm changing k to minus k and taking complex conjugate, u is real, so potential. So this is fulfilled. Okay, let's write down the kinetic energy. This is the kinetic energy. Just took the definition psi r and wrote it down. Because this doesn't depend on r, the only dependence is here. So what do I get?
Like Fourier transforming the Poisson equation.
Like Fourier transforming any equation that has a del square somewhere in it. Could be the diffusion equation, it could be the Poisson equation, it could be anything. The minus became plus because the I squared. Okay, a bit more challenging. The potential part. We know that usually we don't Fourier transform a potential if we don't have some translational symmetry, for a good reason, because it will give us a complicated contribution that won't help anything in the solution. This is very useful if we don't have another part of it. Here it will be useful because although it has some contribution, it's a limited contribution, and therefore we'll be able to pull out a solution out of it. Okay, u times psi. Right, this is the potential contribution. What do? I just copy the two definitions. basically didn't do anything. Just wrote down the Fourier transform of one term and the other and multiplied it. I don't like this term. I want to change it for a particular one wave vector here. So I'll define it Q prime. What's written here? Okay, since this is a mute summation index, can get rid from the prime here. Okay, so what's the Schrödinger equation? Combination of these two things equal E times the wave function. Needs explanation? All I did is take the E times this guy times CQ that was on the other side and moved it in, and it's equal, okay, equal 0. That's all I did.
Where is the Fourier coefficient in the second term?
It's going to be in the
This is on everything. Sorry, it's close it. Good. So I'm left only with this guy is equal to 0. Okay. I want to do a transformation. What can I say about you?
U of k is equal to U of k plus g, right?
Right? What will happen everything must stay the same. The fact that I'm integrating on one cell or another cell shouldn't make any difference, right? So this should be equal to
It's a reciprocal lattice vector, okay?
mm-hmm.
Meaning we can get rid of an integral if we want.
Okay, let's do it one step at a time. Do it in 2 steps. Then put it. Then I'll get here, if I'll put here r prime and put here r prime minus r. So k must be a reciprocal vector, otherwise I'll get a different result on what cell I'm integrating. So k is G. It's not any K, but a specific set of reciprocal wave vectors. Physically, what happened here? Even not physically, mathematically. To describe the whole plane that I had it in the beginning in R space, I needed some number of R's depending on its size, right? If I Fourier transformed it, I got the same number of K's correspondingly. Now I look at a cell. The cell is still, I have an infinite number of R's there, but I already don't need all the K's to describe it, because I have just a finite portion of it. G is also infinite, so it's not that I lost the information, but I don't need any K, I need only K's that correspond to G. So what? Let me now rewrite our good old friend here. Here I just wrote K in general, but it has to be G. Zero. Let me write down Q equal can do it. Let's check if I didn't prime here the wrong G. Everything else is okay. What did I do? Remember the beginning. We had CQ times E minus IQ. Here I basically write down the here I have an equation on C K minus G, and I Fourier transform the solution. Right? So what did I gain by it? Which is exactly Bloch's theorem. E to the power I k dot r times some function. Here I even gave the form of this function. Solve this equation, get these C's.
Well, in a tricky way, you're saying that this is a Fourier transform. You can say it's any function.
No, the truth is, the deep point is that the only reciprocal wave vectors come into my Schrödinger equation.
Right.
Components of the potential. And therefore, you can move it always as function of the potential. That's all it says. It was just rewriting. Okay, so what is K? K is any vector that appears in the first Brillouin zone. If the system is infinite, it's any K in the first Brillouin zone. If you have periodic boundary conditions, it's the points that correspond to these periodic boundary conditions. Second, is K connected to P, to the momentum? Well, not directly, because so if I want to write the operator P working on psi, here I'll keep the N and K. By definition, just wrote down the Bloch theorem. So P is not necessarily h bar times k for a lattice. It has an additional contribution. Okay, we put here very general solutions. Now we'll see two explicit solutions that actually map our potential landscape from two different points. And since they will behave very similarly, we would claim that we understand what reciprocal potential will do for any potential. Okay, what are the two limits? Well, both of them we want to approach from the point of view of perturbation, because that's all we know to do. But we can consider here two different types of perturbation. One is that I assume that I have a very weak potential. And then that's very natural to treat with perturbation theory. Every small correction to the Schrödinger equation, every weak potential.
This is the quasi-momentum.
This is the quasi-momentum. You see that K is not exactly momentum. The other limit, and that we'll do shortly, perhaps not finishing this lecture, but the other limit is, let's think about atoms. Well, at the end of the day, any lattice is built out of atoms. Okay, what is a lattice? An array of atoms. So basically, instead of having one atom in my game, which is a hydrogen atom, I have an array of atoms at the lattice points. Physically, what physical process can come into the game here?
Electrons moving through atoms.
And how do they do it? Tunneling. That's the only way that they can do it. So I will assume that the atoms are relatively far from each other. Therefore, let's say, since tunneling dies out exponentially, only nearest neighbors will be relevant. And I'll use that as a basis for my perturbation. Putting in tunneling, and that's known as tight binding. Actually, the physical, both methods will give me energy bands. While a free electron can be in any energy, electrons in a lattice have regions where they have allowed energies and where they have forbidden energies. To get it from the weak potential, which is also known as nearly free electrons, it's harder to see, although mathematically we'll show it. For a physical intuition, it's easier to see how it comes from the tight binding. Okay, what are the solutions for the hydrogen atom? Or any atom? Basically a discrete set of energies, right?
Depending only in n.
Right, depending only on n. Okay, schematically wrong here. We stick another atom and another. They tunnel. Now, it's very hand-waving, we'll do it much more exact. What happens when I tunnel?
Which sense?
When I take a... What did I have for a hydrogen atom? I put here an electron at some level. I'll come back in 2 days. Where will I find it?
Same level.
Exactly where I left it. Here it can tunnel, meaning that I have some kind of I'm lacking knowledge where will I find it, right? So what's that? Heisenberg's uncertainty. So I'm leaving it here, and it can move to here or here or here. So the energies that were previously sharp, now you have a set of energies around the original atomic level.
But that allows us to locate them in momentum, right?
And that becomes momentum because it can be in any point. So I get a band of energies corresponding around the original levels of the atom. So I get a band and a gap. If they are very close, perhaps the gap closes up. Yeah.
But why can't they jump to the same energy level just in the atom next door?
That's what they are doing. But then if I measure it here, at a different time it's not here.
It's in another atom, but the energy is the same.
We'll do I said that it's very hand-waving, the argument. But no, at the moment that if you want to think about if I add two levels, degenerate, and a small perturbation between them. Or if you want, E0, V, V, right? What would be the energies?
Plus, minus.
You know to diagonalize such a matrix. So it's E0 plus minus V. If V is small, so this is exactly this type of picture. You build two levels, and here you build infinite levels, but since the tunneling is small, the perturbation is small, you don't get it spread all over, it's some finite region.
And actually, due to Pauli exclusion, you cannot go down.
Let's not do too much in one go. Okay? This is the point of tight binding. So you have bands and gaps.
What is the distance approximately between
A few angstroms. And we know that the wave function dies out on a few angstroms.
It's on the same scale.
It's on the same scale. No, it's not by chance. That's the reason why lattices have this scale. Okay, so the other way around. We have a free electron, but a weak free electron. A weak perturbation. Okay, what is a perturbation? For a free electron, if I had a parabola at k equals 0, went to infinity. But here you have an additional parabola. At k equals g, because it's the same. Right? We'll do it explicitly, as I said.
Why parabola?
Because it behaves like k squared. Even here we are left with this q squared behavior. And now I do perturbation theory. So the guys here are not much affected by weak perturbation. Where are they influenced? At degeneracy points. That's the point where the perturbation theory is the most specific. And what does usually perturbation do? Splits the degeneracy. Meaning that this point becomes something like that. Band and gap. Here the gap is large because I started from far away and strong potentials. Here the band is small because I started from a weak potential. But the idea is that the fact that I have a lattice create bands and gaps is essential in both of them and is the feature of any lattice potential. And anything in between will have some complicated structures that depends on the potential but that's details. Then we'll get to the point on how are these filled up by Pauli's exclusion principles that will close up the whole game. In a nutshell, for insulators and semiconductors, they fill up a band and the next open band is above the gap, which creates particular behavior. For metals, the Fermi energy is within the band, which enables a different kind of behavior. Okay, let's stop here and continue the perturbation, both perturbation theories in the next lecture.
So